Hello students and welcome back to my channel. So we are now discussing questions which were asked on 31st of January 2023 JEE mains. So the remaining questions I have already posted. So in continuation with that, we are into question 33. The drift velocity of electrons for a conductor connected in an electrical circuit is Vd. The conductor is now replaced by another conductor with same material and same length, but double the cross-sectional area. The applied voltage remains same. The new drift velocity. Now we have a formula for drift velocity which states that drift velocity is equal to I upon NAE. Remember this? I hope most of you might be knowing this. And this current can be written as I by A can be written as G. Current per unit area is the current density. Also, if you write Ohm's law in microscopic form, it will be J equal to sigma into E. So J can be written as sigma into E, where E is the electric field, and electric field can also be written as the potential gradient. So that is the fall in potential per unit length as you move in the direction of current. Now you see students, the conductor is now replaced by another conductor with same material. So material same means what? The conductivity remains same. Free electron density is same. Electronic charge is same. Length is same. And the applied voltage remains same. So you can see none of the parameter changes. So the drift speed will not change. Moving on to the next question. For the given circuit in the steady state, we have to find the potential difference between B and D. Now here you can see that here the only path available for current flowing is through this 1 ohm resistance. So basically current will start from here. A part of it will flow through this via 1 ohm resistor and the remaining will pass through this and both of them will combine here. Now if I take this current as I1 and if I apply Ohm's law, Kirchhoff's second law to this loop, to this complete loop, if I apply Kirchhoff's loop rule, then I can simply say that I1 will be 6 upon 2 plus 1, 2 plus 1 that is 3. So 2 ampere current. Similarly, if I take this current to this as I2 and if I again apply Kirchhoff's voltage law to this loop, then I can write I2 as 6 upon 10 plus 2 that is 12, half ampere. Now, let us go from B to D. So starting from B, I can write potential as VB. Then going against the direction of current, potential increases. As per Ohm's law, the rise in potential will be I into R. Here I1 into R. So I1 is 2, R is 2. Then as you move in the direction of current, potential reduces. So minus I2 into 10. So I2 is half into 10. We reached point D. So potential corresponding to that point is VD. So we have VB minus VD is actually 1 volt. So answer is 1. Then moving to the next question, an inductor of 0.5 millihenry, a capacitor of 20 microfarad and resistance of 20 ohm are connected in series with a 220 volt AC source. If the current is in phase with the EMF, the amplitude of current of the circuit is root x A. The value of x is so here we have to simply find the amplitude of current, that is maximum value of current. Now it is clearly given that the current is in phase with EMF. So in an LCR circuit, if current is in phase, means the circuit is in resonance. It is a series LCR resonant circuit. So in resonant circuit, the net impedance is simply equal to R, because the net reactance remains 0 there, because XL is equal to XC. Okay. So that means if we want the current amplitude, okay, we can find RMS current first as Vrms upon Z. Z is R here. So Vrms is 220 volt, and resistance is how much? Resistance is 20 ohm. So we have 11 ampere. But we have to find the peak value of current. So peak value of current is nothing but Irms into root 2. So basically it is 11 root 2, which can be written as under root 121 into 2, that is under root 242. So X is root over 242 ampere. Moving to the next question, an alternating voltage V equal to this much is connected across a pure inductive reactance of the circuit. This is a simply formula based question. Inductive reactance is simply equal to omega L. Omega is nothing but the coefficient of T in the equation for current or voltage. So coefficient of T is 628 and inductance is 5 milli. Milli means 10 power minus 3. Now this, instead of multiplying this, I can write 5 as 10 by 2. Okay. So the 0 0 gets cancelled. We have 2 3s are 1s are 4s are. So 314 divided by 100 is 3.14. So the option is the correct option. Then moving to the next question, an amount H of thermal energy is developed by a resistor in 10 seconds when a current of 4 ampere is passed through it. If the current is increased to 16 ampere, then the thermal energy developed by the resistor in 10 seconds. So the thermal or the heat energy produced is equal to I square RT. This is what we know this, isn't it? So here T is same in both the situations. T is same. Also, the resistance is also same. So we can say H is proportional to I square. H is proportional to I square. So let us find the factor of change for I. Factor of change for I is 16 by 4 whole square. So H will increase to 16 times. So D option is the correct option. Okay. Factor of change for H is 16. We calculated the factor of change for H from the factor of change of I. Then moving to the next question, a series LCR circuit consists of R equal to 80 ohm, XL equal to this and XC equal to this. The input voltage is this, amplitude of current. So if we want to know the current, we should know the voltage and the impedance. Now impedance is actually equal to under root R square plus difference between XL and XC whole square. Difference between XL and XC is nothing but the net reactance. So this is 80, whereas this will be 100 minus 40, that is 60. And we all know that this is 100. So therefore, current amplitude, that is peak value of current, is peak value of voltage by Z. Peak value of voltage is 2500 upon 100, which will be equal to 25 ampere. Then moving to the next question, two identical cells when connected either in parallel or in series give same current in an external resistance 5 ohm. The internal resistance of each cell will be. So we have two different situations, students, here. In one situation, the identical cells are connected in parallel, and in another they are connected in series. In either cases, the current through an external resistance is same. So we have to find the internal resistance of each cell. Right. So in the first case, let us say the two cells both are identical, are connected like this. Let us say internal resistance is R, which we have to find. EMF, I will take it as E. Okay, so these two cells can be replaced by a single cell of equivalent EMF. When identical cells are connected in parallel, equivalent EMF remains E itself and internal resistance becomes R by 2. So this is equivalent to this. I have replaced both the cells by their equivalent EMF and equivalent resistance. So this is the situation. So here the current will be equal to EMF upon total resistance of the circuit. Now for the second situation, when the cells are joined in series, when the cells are joined in series, then simply can write the current as total EMF upon total resistance. Okay. As per the question, both these are equal. So if we equate them, then we have E upon R plus R by 2 is equal to 2E upon capital R plus twice R. So cancelling E both sides, we can write R plus 2R is equal to 2R plus R. So small r is equal to capital R. So capital R is already given as 5 ohm. So the answer should be 5 ohm. That's all students in this video. Thank you for watching.